For thousands of years, mankind has been drawn to caves and caverns in search of shelter and raw materials. But it's only recently that we've exploited underground space on a large scale and not just for minerals.
In this program, we travel to Norway to see the largest rock cavern in the world in public use and visit the deepest excavation ever undertaken in London as it nears completion. But we start at the deepest mine in Western Europe on the northeast coast of England. This is Boulby, on the edge of England's Yorkshire moors. It's home to Britain's only potash mine, supplying the mineral potassium chloride, essential to agricultural fertilizers. It's a relatively modern mine and uses pioneering techniques for creating underground space. For centuries, mining has presented us with the same problems and dangers. It's not easy and it's not pleasant, but if you want the treasures of the earth, then you have no choice but to go deep underground.
Right, let's go. It's a hostile environment. Mining is difficult and potentially dangerous work. But if you're successful, it's a lucrative business. The challenge is how to dig away at the very matter that's holding the roof up above your head. Thank you. To get to the potash seam, we have to travel over 1 kilometre down into the Earth's crust and then drive 8 kilometres out under the North Sea. Great. Thanks. Right, let's go.
We're now in a pre-Triassic world. The seam that they are mining was formed as part of the bed of a prehistoric sea which reached as far as what is now Poland.
This sign marks the end of the coast. From here on, we're under the sea.
It takes half an hour to reach the face. It may look dank and dingy down here, but it's actually incredibly hot, 40 degrees centigrade. The reason is we are closer to the molten rock beneath the Earth's crust. Not much closer, but enough to make the difference.
Yesterday, this was solid rock, which had been sleeping here for hundreds of millions of years. And by the end of the day, they'll be 7 meters further on. In a few weeks' time, it'll all be gone. It may seem that they're just boring away, but in fact the tunnels are part of an ingenious structural design which combines geology and engineering expertise to create a controlled and safe space.
This space is supported without any additional propping. Instead, they create the supporting structure by carving out the existing rock into pillars and arches, just like a church. The weight from above is channeled to the carved rock pillars on either side. The really clever part comes in creating a single super arch to span over the individual arches of several tunnels.
It works like this. This is the seabed, way above us. If you drive a single tunnel by itself, then a small arch forms naturally over the top. But the weight of the rock above, all the way to the surface, is still bearing down on it and squeezing in from the sides. Driving several tunnels together can solve this problem. What happens is that as the roof starts to sag, a giant arch forms naturally right over all the group of tunnels together, throwing the weight from the rock above out to the sides. It's still squeezing in, but not in the middle. That leaves this section here, which is now detached from the rock above. It's bearing down on the tunnels in the middle, but now the force is much less. The walls between the tunnels are allowed to crush slightly as the roof bears down. Here you can see the cracking of the rock vertically. Eventually that will break away, leaving an apple core shape like this, tapered in the middle. Of course, all this rock is like money to the mine. The incentive is to excavate everything that can safely be removed.
Striking the right balance between how much to excavate and how much to leave as support depends on constant and thorough geological study. Just looking at the appearance of the exposed rock can reveal a lot about how it was formed and, critically, how it will behave.
All these rocks are sedimentary. That means they were laid down as loose grains and eventually squeezed together to make rock. 240 million years ago, all this rock was being formed on the seabed. These layers show the sedimentary process, winter and summer, as grains fell to the bottom of the sea, exactly like the rings on a tree.
The geologists also send probes down boreholes drilled at precise inclines into the rock face. These provide essential information about the direction of the potash seam and how wide they can safely excavate the tunnel. A graph is drawn of what lies ahead, and precise instructions are painted onto the rock face itself for the miners to follow.
Here we can see the roof of the tunnel sagging and starting to collapse under the weight of the rock above. It looks risky, but the whole life of the tunnels and the space can be mapped out, provided the geology is thoroughly understood. And here you can see the final result, the collapsed roof. It's been allowed to collapse to protect the working tunnels next door. It may stay like this forever, or it may eventually converge, squeezing together. The Boulby mine is a leading example of the latest in mine design. Here they're creating space for a very specific purpose and for a short duration. But it isn't a place for the public. If you want underground space which the public can use, it has to look rather different.
This is Gjøvik, a small town 140 kilometers north of Oslo, an historic trading centre on the shores of Norway's largest lake. In 1988, it was announced that the Winter Olympics would be held in Norway in 6 years' time. Gjøvik was chosen to host part of the ice hockey competition. Top of the to-do list was build a stadium. In a small town like this, a conventional stadium here on the surface would have stuck out like a sore thumb. Building it underground would solve that problem.
The challenge was how to create an underground space vast enough for an Olympic stadium. You enter the Gjøvik Stadium through a 120-metre-long tunnel which runs deep into the mountain. The lighting is specially designed to give you a feeling of entering a subterranean world. Compared to the rough and dirty environment of the mine, this is almost clinical in its cleanliness.
The Mountain Hall at Gjøvik is one of Europe's most extraordinary civil engineering achievements. This ice rink is the largest rock cavern for public use anywhere in the world. Walking from that tunnel into this huge space is quite magical. This is a stadium with seats for 5,800 people, but we're 50 meters below the surface of the mountain. The whole space is wide enough for a football pitch and tall enough for an 8-story building.
Normally, you associate underground space with being small and close, but this is quite the opposite, light and spacious.
This is because the huge roof needs no columns or props to hold it up, so the space underneath is absolutely clear. So how did they create this permanent space and stop its vast roof from falling in?
It may be big, but it's been built using tried and tested techniques. This is the mountain and the cavern with its rounded roof. The natural fractures in the rock above break it up into blocks which could fall down. To prevent this happening, the roof is strengthened using rock bolts. These are steel bars pushed into holes drilled deep into the roof and cemented in position. By locking the whole roof together, they create a sort of dome over the cavern, and this is the ideal shape to carry the weight of the mountain safely to either side. Tusen tack. I can show you how the rock bolts work with this lump of Norwegian cheese. It's very simple. Like loose bricks, the blocks of rock in the roof would fall down over time if they weren't held firmly in position. The bars link all the blocks together so they can't move independently. So effectively, the rock mass acts as one and is locked together in 3 dimensions by the bolts. It's a lovely igneous rock called gneiss, funnily enough. Beautiful red colour. And that's a hole for a rock bolt, right there. And here's another one where you can actually see the steel tendon sticking out of the rock and the cement around it where it's been set in place. This one's been cut off so that people don't tear their clothes when they walk past. Up here, I'm between the metal skin of the roof and the rock itself. This is one of the rock bolts just sticking out over there. The metal roof is hanging from the rock on these blue bars that you can see in the distance. They excavated the cavern by drilling and blasting. 29,000 truckloads of rock were taken away. It's amazing. One of the great advantages of building underground is that the ground insulates the space. Down here, the rock is an absolutely stable 8 degrees centigrade. That's a lot warmer than outside.
The temperature of the seating areas and corridors is easily raised above this rock temperature to a very comfortable 16 degrees centigrade. This is achieved by recycling the waste heat produced by the ice refrigeration machines.
It's much colder on the ice, and that's largely because the silver reflectors up above bounce the cold back down again and keep this whole area freezing. In fact, being underground is very economical. Energy consumption is just 50% of a conventional stadium, and maintenance costs are minimal because it's entirely protected from the elements. The stadium has another side to it altogether. It's designed as an air raid shelter for the town, capable of taking 2,000 people. The whole complex can be sealed off using these huge doors, and life support systems can protect the occupants for up to 48 hours.
The Jurvik Cavern is an outstanding example of how engineering underground can create an excellent leisure space for the general public.
But in reality, few of the major cities in the world are built on rock. When it comes to digging down in soil, an altogether different approach is needed, as we shall see next.
London is one of the greatest cities in the world. It's exciting, busy and congested, with fewer and fewer sites left for essential new buildings.
One solution is to build upwards, but another, as we saw in Norway, is to build downwards, exploiting that space underground. This is the new underground station at Westminster, in the final stages of completion. Under this ticket hall is the deepest excavation ever undertaken in London, the same height as a 12-storey building entirely underground.
The station is being rebuilt to accommodate the extension of London's most modern underground railway line, the Jubilee Line. With sites such as Big Ben and the Houses of Parliament next door, it's destined for heavy use. In fact, 10,000 passengers will pass through these gates every hour. Tunnelling the rail link is comparatively straightforward. The daunting part would come in digging a hole big enough for 4 lifts, 6 staircases and 17 escalators. Holding back the earth from such a vast space is especially difficult here, where the soil is almost pure clay. This clay is not only soft, but also sponge-like, prone to swelling as it draws up water from all around.
The challenge for the engineers was to build this huge new station complex deep into the clay soil underground without disrupting the existing station and, critically, without threatening the foundations of its famous neighbour across the street.
The obvious shape for the structure was a giant box protected by deep walls on all sides. Simply digging a big hole for the box would be very risky because the sides would cave in. The trick is to put the walls in first.
Here I can show you how it's all laid out. This is ground level. The deep slots were made in the ground around the box, like this. Steel mesh was dropped in, and the slots were filled up with concrete to make the walls. Of course, there's still soil inside, and if they'd started digging now, the walls would have caved inwards. So they had to build the floors first to keep the walls apart. This meant they had to start at the top with the top floor, and then they dug out the soil underneath and fitted a strut. And then they dug out the soil underneath that, fitted another strut, and so on, right the way down to the bottom. In fact, it's so deep, you could almost fit the Tower of Big Ben inside. This is the deepest underground space in London, and yet it feels more spacious than many ordinary buildings. It's only possible because of the ingenious system of struts and walls that allow this great box to be built deep underground. The wall around the box, which was built first, is called a diaphragm wall. It's made of reinforced concrete, and it goes all the way from the ground surface down to below the bottom basement. It has to withstand the pressure from the soil and the water in the ground outside, which is constantly trying to push it inwards, so it's over 1 meter thick. It looks rough, but of course the concrete is just poured into a slot cut in the ground, using the clay itself as the mold, and then that soil is just dug away, leaving this surface. It's very impressive, really. The diaphragm wall is further stiffened by these concrete buttresses, which run up and down, and beams which run from side to side. And they carry the force from the ground outside into these huge steel struts, which span from one side of the box right across to the other. They each weigh 60 tons, and it's 24 meters across the width of the box. Using struts like these allows the space inside to be as clear as possible, which is what the designers wanted, a feeling of openness. Even here, deep underground, you can see right up and down the building.
This great underground structure in fact does more than hold back the wet London clay. It also provides a solid foundation for new construction on the surface. 6 floors of a new parliamentary building are being stacked above the station. The ingenious underground box design is a template for metropolitan development. It proves that anywhere in the world, even with limited space on the surface and soft soil underneath, buildings may be constructed both above and below ground level without creeping into the skyline or sprawling into the countryside.
Our understanding of how to work with soil and rock has developed massively over the years. From tunneling mines and excavating rock caverns like the one we saw in Norway, to the sophisticated solutions for building deep under metropolitan London, our technology has advanced to meet society's every demand. There is huge potential for using underground space even more in future. What's exciting for me as an engineer is to meet that challenge, to create that space.